Okay, another example here, drawing the Newman projection of all staggered conformations of 1,2-dichloroethane. This is the answer for these two problems. Please go ahead and look at these two problems in here. And again, every time you draw your Newman projection, make sure to locate your carbons in front and the carbons to be behind. So here, if I am looking this in this direction, I can look in the other direction and have this carbon to be in front, but I'm looking in this direction here according to my drawing. So this carbon is going to be in front. This is going to be carbon number 1 in front. So carbon number 1 in front, I'm going to fix for the whole, for all of them. Okay, so as you can see, I can fix for all of them. There's an easy way to draw it. Simply draw carbon number 1, the circle, and carbon number 1, the same for all of them. Okay, and then carbon number 2 is going to be the circle at the back. That is going to be carbon number 2. That is in the substituents in green. And carbon number 2 has chlorine in there. See how the big groups, I put them over the vertical line just to let you know that this guy now is going to be anti. So this is going to be anti here. This is going to be anti. And this is going to be eclipse. E stands for eclipse. This is going to be gosh. The big groups are 60 degrees away from each other. Of course, the energy here between the two chlorines is going to be different than the energy between the two CH3s. And normally, if I want you to calculate the energy, I would go ahead and give you the energy value for them. This is going to be the fully eclipse, okay, where you actually have the torsional strain and the steric strain at the same time. Here, this is the gauche again. So this is gauche, and here this is eclipse, and then you go back to the anti. So see, I don't have more than 6 conformations. This is the maximum number of conformations in here. So simply draw it as you see it. Carbon number 1 is in front, carbon number 2 is behind. Always whenever you wanna you want to go from one conformation to the other, you rotate. Make sure you fix one carbon, you rotate the other, fix whatever carbon you want, but just fix one and rotate the other. When you do a rotation 60 degree at a time if I ask you to draw all the conformations. Same thing over here. I'm asking to draw all the conformations, so go ahead and just do a rotation 60 degree at a time. Now, with respect to this problem over here, this is 1-phenyl propane. This is going to be my phenyl group. My phenyl is the benzene. It's on carbon number 1. This is a propane, and I'm asking you to draw the Newman projection between carbon 1 and carbon 2. So basically, the Newman projection is along this bond over here. Looking at it, I am looking at it to view here my carbon number 1 to be in front. So I am making carbon number 1 in front. That means carbon number 2 with the CH3 behind. So 2 with the CH3, that is going to be behind. And then fix carbon 1. It's always easier to fix the front carbon, rotate the back carbon. If you want the opposite, it's fine. It's not a big deal. So the structure, the question in both, it says which one has the lowest for number 2, lowest energy, lowest and highest energy. So the lowest energy is going to be the anti, and the highest energy is going to be fully eclipsed. No need for you to know the energy values, because I know here that anti is low in energy, is the lowest in energy, is the most stable, and the fully is the highest in energy, which is the least stable. Same thing over here. I don't need to give you any energy values because you have only 2 substituents in there. So you have the 2 big groups. You have the phenyl and you have the CH3. So these two, when they are 180 degrees away from each other, this is the anti. So the anti is going to be the lowest uh, energy, so it's going to be the most stable. So this is going to be the most stable in there. Okay, now the question is, draw the most stable conformation of 1-phenylbutane. I drew all of them, but this is not actually the question, but I wanted to show you all the conformations of 1-phenylpropane. they are asking about the most stable. So the most stable is going to be this guy over here. This is going to be the most stable. And they are asking me to change the Newman projection into a Sawhorse. So for the Newman projection over here, okay, here you go. Let's change it into a Sawhorse. So for the Sawhorse, this is how it's going to look like. I know that I have a fennel here. It's pointing down. I do have a hydrogen here on the side. This is in front. I do have a hydrogen at the back over here. This is the hydrogen at the back. In this case, I am viewing it from the side. This hydrogen is at the back. And then I do have a CH3, okay, on top here. Then this hydrogen is going to be, this hydrogen over here, it's going to be on this side. And this hydrogen over here is going to be at the back on that side over here. Again, the angle between this hydrogen and this hydrogen is going to be a 60-degree angle, and the angle between these two hydrogens are 60 degrees. You can easily see that when you build your molecular model. As we mentioned, whenever you draw a chain conformation, and we saw that the lowest energy conformation has all the bonds are staggered to each other in all the larger groups. See, all the larger groups, they are anti with respect to each other. So between these two carbons, the larger groups are anti with respect to each other. Between those two carbons, the larger groups are anti to each other. This is the larger group in here, and this is the larger group in here, and they are anti with respect to each other. So this is why when we represent a chain of carbons, we represent it in a form of a zigzag skeletal structure. So this is going to be for the conformations of alkanes. Now for the conformations of cycloalkanes. So for conformations of cycloalkanes, so far we know that with alkanes there are two forms of energy strain that we have to normally take into consideration. The torsional strain, which is caused by eclipsing of the bonds, and the steric strain, which is caused by the London forces or the van der Waals forces whenever two groups they come close to each other, as in the case of basically gauche. Whenever you have two CH3s or whenever you have two Cls in there, they will have some van der Waals interaction. Or if they are zero dihedral angle in there, they are very close and they align, they will also have a type of steric strain. That is for alkanes. Now, for the cycloalkanes, I have to add an additional form of an angle strain that of a strain that normally decreases the stability of the structure because it increases its energy, and that is the angle strain. The angle strain normally is defined as a strain which is due to the expansion or compression of the bond angles when deviated from the normal tetrahedral bond angle, which is 109.5. Let's take a look at it. Normally cycloalkanes, when we draw them, when we represent them on paper, we represent them in a form. This is a three-membered ring cycle, cyclopropane. This is cyclobutane, this is cyclopentane, this is cyclohexane. Now, the way that they are represented on paper, they are represented as being a planar, all of them, meaning that all their carbons, they lie in the same plane. All their carbons, all their three carbons, they lie in the same, here all the three carbons lie in the same plane. It has to be, it's basically a planar structure. However, if you take a close look at the hybridization of each of these carbons in there, the hybridization is not trigonal planar. The hybridization is an sp3 hybridization. So this means that the bond angle, I have a hydrogen here and I have a hydrogen in there. This means that the bond angle between the hydrogens is going to be 109.5. Okay, so the bond angle between the carbon hydrogens, this is 109.5 in this case. Now, but what I see is when these carbons are packed with each other, the bond angle is really deviated. It's compact. It's really deviated from the 109.5. So instead of being 109.5, it's 60 degrees. So it is basically compressed. It's basically compressed 49 degrees. It's compressed 49 degrees in order to reach that 60 degrees. So imagine the angle strain that the cyclopropane undergoes. Cyclopropane undergoes a lot of angle strain because it is hugely deviated from the 109.5. Now, with respect to the cyclobutane, has it should have a bond angle of 109.5, but in reality it has a bond angle of 90 degrees. So it's deviated. The bonds are compressed. It's deviated by 19 degrees from the 109 ideal tetrahedral angle. Again, all of these carbons are in sp3 hybridization. So ideally you should have ideally here you should have basically a bond angle of 109.5. Now, with respect to the cyclopentane in here, this is basically, again, the bond is compressed, but it's not compressed much. It's just 1 degree from the 109.5. In the cyclohexane, the bond is expanded, or the bond angle is expanded 11 degrees from the 109.5. The point is, this expansion and compression of the bonds is going to cause an angle strain, and this angle strain is going to increase the energy of our structure. So increasing the energy of our cycle is going to make our cycle basically less stable. So the cycle is going to try to arrange its carbons in a way to relieve the angle strain a little bit. So this is why 1 or 2 carbons from these cycles will be pointed out of the plane. And that type of conformation, we call it a puckered conformation. That type of conformation normally is needed. And this type of conformation is needed just to make sure that the cycles exist in their most stable conformation. Let's start with each one alone. So a cycle of 3-membered rings in there, the angle strain, it's caused by 60-degree carbon-carbon-carbon bond angles. And this type of cycle, 3-membered ring cycle, it has all of its carbons, they lie in the same plane. This is going to be the most strained of all the rings, since this is a planar structure, although each of these carbons is an sp3 hybridization. It does have 2 types of strains. It has an angle strain and it has a torsional strain. The torsional strain is here, it's due to the eclipsing of the bonds. What I did, remember, a Newman is between 2 carbons, so I cannot draw a Newman for all the carbons. So I'm going to draw a Newman between these 2 carbons over here, and you can see that the 2 hydrogens here, they eclipse each other, and the 2 hydrogens here eclipse each other. So this is where my torsional strain is. So cyclopropane has 2 types of strains. It has an angle and it has a torsional strain. Normally the compression of the bonds is going to make basically those sigma bonds in here around the carbon, single bond carbon, very weak. Now, remember that these compression of the bonds, these are the result of the hybrid bonds. This is the result of the 2 hybrid sp3 hybrid orbitals that are overlapping with each other to make the sigma bond for each of these carbons. So I have a hybrid orbital here, a hybrid sp3, and a hybrid sp3 over there. They are overlapping with each other. They are making a sigma bond. But because the hybridization is not an sp3 hybridization, in this case, my sigma bonds are going to be bent bonds. They're going to be very weak sp3 bonds, very weak bent bonds. So these weak bent bonds can be broken very easily. This is why we say that cyclopropane is very reactive, because its bonds are very weak. Its sigma bonds are very weak. We can break them easily. The reason why they are very weak, because these sigma bonds are caused by the overlap of 2 sp3 hybrid orbitals, and these hybrid orbitals are bent because they cannot assume the 109.5 bond angle. They are making a 60-degree bond angle. So they are bent in order to do this. They are forced in order to do that sigma bond, that overlap interaction in there. With respect to the cyclobutane, again, I have an angle strain and I have a torsional strain, but the difference here is the cyclobutane is a 4-carbon cycle. So now I can decrease the energy a little bit of my structure by taking 1 carbon out of the plane. So see that carbon over here? I can take it out of the plane, and I'm showing it pointing up. Pointing up means that it's basically out of the plane pointing towards you, and we call this type of conformation a puckered conformation. So that puckered conformation is going to relieve the energy a little bit, the strain a little bit, and it's going to cause less torsional strain once 1 carbon is out of the plane. So if I'm drawing a Newman projection here for between these 2 carbons, you can easily see that this carbon is pointing out of the plane, so that is going to relieve the energy of the structure a little bit. Same thing for the cyclopentane. It has both angular and torsional, and I can relieve the torsional strain a little bit by taking 1 carbon and pointing it out of the plane. Now the one that we're going to focus more on is the cyclohexane. The cyclohexane is a cycle of 6-membered rings, and the cyclohexane, in order for it to exist in its most stable conformation, I have to take 2 carbons and point them out. I have basically to take carbons and point them out of the plane. So to represent a cyclohexane, I'm going to represent it as a chair conformation. So this is going to be my chair conformation over there, where I will have basically 3 carbons. So I'm going to go ahead and point those out. So I'm going to have 3 carbons. This is 1 carbon, this is 2 carbon, and this is 3 carbons. 3 carbons are going to be pointing up the plane, and I'm going to have another 3 carbons. They are going to be pointing down the plane. Count them all. This is a total of 6 carbons, and this is the most stable conformation, puckered conformation of a cycle with 6-membered rings. So a cycle with 6-membered rings, for naming purposes, we draw it as a planar structure showing all the carbons in plane. But whenever we want to check the stability of the structure, we have to change the cyclohexane into a puckered conformation, meaning I need to show 3 carbons pointing up and the 3 carbons pointing down. So in this case, the way that you draw a chair conformation is basically the following. You draw 2 lines that are parallel with respect to each other, and then you draw basically a point or a carbon up, and then you draw a carbon down, and then you go ahead and you connect all of these together. So you draw a small triangle in here, you draw a small triangle in there. Keep it practicing and you will get it. Okay, so this is how you draw the chair conformation in there. This is the carbon skeleton, and this is the chair conformation. If you have your molecular model set, you can build the molecular model set, and in the model set you can easily see that you have these carbons are pointing up, and then you have these carbons over here, they are pointing down. When we draw the chair conformation is very stable, and the reason why it's stable because it eliminates the angle strain. So you will not have an angle strain in there, and all the CCC angles, they are going to be tetrahedral, and they are going to have the 109.5. They're going to have the 109.5 in this case. You're not going to have the torsional strain, so there will be no torsional strain in this case. There will be no eclipsing of the bonds because all the hydrogens and the carbons, they're going to be staggered. They're going to be far away from each other. So see those 2 hydrogens, they are going to be staggered. They're going to be far away from each other. Now in cyclohexane, we have, as I said, 3 carbons that are puckered up and 3 carbons that are puckered down. And these carbons are going to alternate in the ring. Now, there are 2 sets of hydrogens that we care about, and we're going to use whenever we want to calculate the energy of the cycle. So the sets of hydrogens are defined as either axial or equatorial. As the definition in here, an axial hydrogen is a perpendicular hydrogen, is a hydrogen which is perpendicular along the axis. So it's a perpendicular hydrogen. It can be either up or down. So to represent the axial hydrogen takes basically the direction of the carbon that it is on. So let's have an example over here. You'll see, let's draw it over here. So this is going to be my chair conformation, okay? And let's draw all the axial hydrogens. Please practice these because it's a very important. So drawing all the axial hydrogens, I'm going to draw them in red. Okay, you look at the position of the carbon in there, the direction of the carbon, and the axial hydrogen will basically follow the direction of the carbon. So if the carbon is up, then the axial is going to be up. See how am I drawing up? I'm not drawing it up this way. I'm drawing it up as a perpendicular line. So this is going to be my axial hydrogen over here. Every carbon has an axial hydrogen and an equatorial hydrogen. Let's draw the axial first. So this carbon over here is down. See, that is a down carbon. It is down. So its axial is going to be down as a straight line. This carbon over here is down. Its axial is going to be down as a straight line. This carbon is up. Its axial is going to be up. So this carbon is down, axial down. This carbon is up, axial is up. So notice at the end, what did I have? I had 3 axial hydrogens that are pointing up. And I had 3 axial hydrogens that are pointing down. So the first thing that you draw is the axial. Now once you draw your axial, you can easily fill in your equatorial. And the equatorial hydrogens, these are hydrogens that are located in the plane of the ring. Okay, so they are around the equator. They are a little bit tilted in the plane of the ring. So if the axial is up, see the axial is up, then the equatorial is going to be pointed down. This is down, this is up. To represent an equatorial which is down, it has to be down. So I cannot put it on the side like that. It has to be pointed down because its axial is up. I cannot have axial up, equatorial up. Because remember, this is a tetrahedral carbon. So one bond is going to be up, the other one is going to be down. Okay? And please don't use wedges and dashes because we don't use wedges and dashes in cyclo. In the chair conformation, we use the axials and the equatorials. So on this carbon, I have my hydrogen pointed down. This is my axial. Then this means that my equatorial is going to be up. See, I'm drawing it up. So if the axial is down, then the equatorial is going to be up. Axial is down. Equatorial is going to be up. It can be either on this side or on the other side. It doesn't matter. So this is going to be my equatorial hydrogen. Axial is up. Equatorial is going to be down. See how am I drawing it? Don't draw it inside the cycle. Draw it outside. So that is going to be the equatorial. Axial is down. Equatorial is up. So up and down. So if the axial is down, the equatorial is going to be up. Here the axial is up. My equatorial is going to be down. Okay? So at the end, you end up having 6 axial hydrogens and 6 equatorial hydrogens. Count them. Okay? It's explained in this slide over here. So, cyclohexanes, they do undergo conformation. Now, we explained the conformation of alkanes, which is a rotation around a carbon single bond carbon. For cycles, they do undergo rotation, but the rotation is called ring flipping. So you flip the ring. So as a result of the ring flipping here, the carbon which is pointed up, you just go ahead and you flip that, and now it becomes down. So the up carbon becomes down, and the down carbon, see that carbon which is down, that carbon you flip it and it becomes up. So basically the up carbon becomes down and the down carbon becomes up. Okay? This is how you flip it. You flip it. In this case, there is an intermediate that you go by. There are series of intermediates to go from one chair conformation to the other. So that first chair conformation, we're going to call it conformer 1. And that second chair conformation, we're going to call it conformer 2. Okay. So normally you go from conformer 1 to conformer 2 by simply flipping the ring. Now, going from conformer 1 to conformer 2, you're going to end up passing through a lot of intermediates. These are the shapes of the chair conformation before reaching its most stable energy second conformation. The chair conformations, as you can see, have the lowest energy. These are the most stable conformations in there. Now, by flipping, you pass it through half a chair, twist boat, and then twist boat again, and then half chair, and then the second chair conformation. So normally we don't show any of those. We just show the flipping from one chair conformation to the other. Okay. So as I'm showing over here in this slide, cyclohexanes, they do exist in a boat conformation, and if they exist in a boat conformation, if you build a molecular model for the boat conformation, it's not stable. The reason why it is not stable, because you do have torsional strain, because you do have hydrogens in there on the 4 carbons in the plane that are eclipsed. See those hydrogens here? These, we call them flagpoles. These hydrogens basically are eclipsing each other. They align with each other. And this eclipsing of the hydrogens is going to increase the energy of my intermediate of the boat conformation. So this is why the boat conformation is not considered to be a stable type of conformation for a cyclohexane. Reason why? Because it does have a high energy due to the eclipsing, due to the torsional strain of the CH bonds. So the 2 chair conformations of cyclohexanes, they are different. And there's a big difference between conformer 1 and conformer 2. Sometimes they are not equally stable. So we're going to check the stability of these chair conformations based on the groups that are on the chair conformation. Just one thing that I want you to pay attention to. Whenever you have groups on the axial position, so groups on the axial position here, they do have a possibility if they belong to the same plane. If I'm looking, for example, at this CH bond, this CH bond is up. So and it's axial in this case. So it's going basically to align with this axial bond here, and it's going to align with this axial bond in here, because all of these CH bonds, they are up and they are in the same plane. So basically there will be some sort of interaction between them. So whenever you have an axial interactions, whenever you have groups in the axial position, there is a possibility of 1,3 diaxial interaction in there. And that interaction is going to increase the energy of your chair conformation, and it's going to make it less stable. So this is why we do prefer that the groups be on the equatorial position, because if they are on the equatorial position, they are simply very, very, very far away from interacting with any axial hydrogens. They are completely in a separate plane. So this is why the energy is going to be more stable. So the point is, the more groups are on the equatorial position, the more stable your conformation is. Let's take an example. We are having a methyl cyclohexane. So I'm giving you methyl cyclohexane, and the question is, this is my methyl cyclohexane, and the question is, go ahead and draw methyl cyclohexane in 2 conformations and label which one is the most stable conformation. In order to tackle this question here, what you need to change is basically your structure into a chair conformation. So we're going to start by simply drawing the cyclohexane. Just I'm showing you here how to draw it, okay? So that cyclohexane, that 6 carbon cycle, I'm gonna go ahead and draw it into a chair conformation. This is my first step. My second step over here, I'm gonna locate my substituent. My substituent is on carbon number 1. I can label carbon number 1 anywhere on the cycle. I'm gonna go ahead and label it here and make this carbon number 1, okay? So on carbon number 1, I have my CH3. At this point, I know that I have 2 positions I can put my CH3 on. I can put my CH3 either on the axial or on the equatorial. It does not matter. The axial on this carbon is up. The equatorial is down. So you can start with the axial, you can start with the equatorial, it doesn't matter. I'm going to go ahead and start with the equatorial over here. Okay? So this here, this way, I changed my structure into a chair conformation. The question is, go ahead and do the second conformation of this chair conformation and see which of these 2 conformations is more stable. So to do this, I need to do a ring flip. How to do a ring flip? Let me go back here. Point out your axial hydrogen, your equatorial CH3. To do a ring flip, see that carbon which is up, this carbon which is up, that carbon is going to be down. Okay, so that carbon basically rotate or flip. Let's say flip. So this carbon is going to be down because it was up, and this carbon was down. You see, was down. I'm just gonna flip it and I'm gonna make it up. So now it's up. Okay, now once you flip your carbons, so to flip the carbons, the carbon which is up becomes down, the carbon which is down becomes up. Now you're going to position your substituents. So the group that is on the carbon, where should it be? Now, right now, the group is where? It is down. Do you see it? It is down because the up is the axial. Notice here I'm going with up and down, and this is important. So the up hydrogen is on the axial, the down hydrogen is on the equatorial. Okay, so the down hydrogen is on the equatorial. The CH3 is down. So if it's down, when I flip it, it has to remain down. So now the down position on this carbon has to be the axial. So now the CH3 is on the axial. Point is, when you do a flip, equatorials become axials, axials become equatorials. If you have a group that is pointing down, it has to remain down. So that remains down. However, now it is on the axial position. So now these are your 2 conformations of the methyl cyclohexane. You have a CH3 which is in the equatorial position. You have a CH3 with it which is on the axial position. The point is, which one is more stable? Meaning, which one occurs, where's the direction of equilibrium in this case? And normally the direction of equilibrium is going to be towards the most stable structure. This is the most stable structure. Let's explain why in this slide. So you do a ring flip, and now the CH3 which is down remains down. It's not changing, but now instead of being on the equatorial, it is now on the axial. Okay? Now, in order to check and see which one of these conformations is more stable, I have to consider the energy for both of them. And the energy for both of them normally is formed from the interaction of the axials with respect to each other. The equatorials don't interact with each other, but the axials do. So here I have an axial CH3 which is pointing down, right? So it occupies the plane which is down. So all the hydrogen axials that are down are going to interact with the CH3. I have 2 of them because this carbon is down and this carbon is down. So it has an axial hydrogen down, it has an axial hydrogen down here. Two hydrogen axial CH3 interactions over there. These are, each one is going to be 0.9, so I have a total energy of the structure to be 1.8 kilocalories compared to this conformer here that has no energy. So the CH3 here will not interact with any axial hydrogens. The reason why? Because the CH3 is in the equatorial plane. It's a separate plane from the axial. Interactions only happen in the axial position. They cannot happen in the equatorial position. Unless you do have a gauche conformation, then you have an equatorial interaction. If you have two CH3s that are gauche, so if you have a CH3 down and a CH3 up here, then you're going to have a gauche interaction between the two CH3s. Then in this case, you have an energy interaction. But other than that, interactions happen with axial groups. So since this structure over here has an energy 1.8 kilocalories per mole, conformer 2 is going to be less stable than conformer 1, so the direction of equilibrium is going to be towards the more stable conformer. So this exists in a higher percentage than conformer 2. This means that whenever you have a structure and that structure has substituents on it and you want to change it into a chair conformation, you guys, please make sure to put as much groups in the equatorial position as possible. Okay. So this is the molecular model in here, just showing you that the CH3 is in the equatorial position. And if it's in the equatorial position, it does have more room in this case, so it's far away from any other interaction. That CH3 is in the axial position, is going to interact with the two axial hydrogens that are in plane, in the same plane as the CH3 pointing down, increasing the energy of this structure. If you have a bulky group, like a tertiary butyl group, please make sure that that bulky group is always on the equatorial position. It does not exist in the axial position, because in the axial position the structure is going to be highly destabilized. You're going to have a steric strain in this case, and that strain is going to be due to the 1,3 diaxial repulsion. So this is why avoid having bulky groups on the axial position. Always make sure that they are in the equatorial position. Let's have an example. If we have before having an example, let's explain the terms cis and trans. When you have substituents on the cycle, if you have two substituents on the cycle, not more than two, so cis and trans are definitions of substituents on the cycle that are basically two of them, and these substituents can either exist in plane or they can exist in opposite planes. So if the CH3s are in plane, they can either be represented in front or behind. So I can simply represent them like this. Okay, I can represent the CH3s being behind like that, or I can represent them to be in front. This means that these two CH3s are still on the same side. They are on the same side behind, they are on the same side in front. Or I can represent the CH3s in opposite planes. One in front, the other one is behind. Or I can do one behind and the other one is in front over there. This is called a trans isomer. This is called a cis isomer. These are two different isomers of 1,2-dimethylcyclopentane. These isomers, we call them stereoisomers. They are a type of stereoisomers. Stereoisomers is a broad definition of isomers that basically have the same molecular formula, but they have different arrangement of atoms in space. So far we've seen conformers to be a type of stereoisomers. Another type of stereoisomers is basically the cis and the trans. The cis and trans is another type of stereoisomers where now we are looking at the groups, two groups on the cycle, And the two groups, by the way, they can be either on adjacent, two substituents can be either on adjacent carbons or they can be on different carbons in the cycle. It doesn't matter. So I can have a cycle of 6-membered rings and I can have a group here and I can have a group there. This is 1, 4. So I can have a group on carbon number 1 pointing up, a group on carbon number 4 pointing down. Since they are opposite to each other, this is called a trans isomer. If they are on the same side, then this is going to be called a cis isomer. The point is, cis and trans, these are type of stereoisomers. We call them geometrical isomers. And these types of isomers, they basically differ in the arrangement of atom in space. You can never, ever, ever, ever go from cis to trans by rotation. So if you build a molecular model and if you rotate this molecular model in here, no matter what direction you rotate that molecular model by, you can never go from cis to trans. The only way to go from cis to trans is to simply break this bond. You break that sigma. You need to break the cycle to go from cis to trans. This is why I'm calling them geometrical isomers. They are not conformers. Not conformers. You cannot rotate to go from cis to trans in there. So A and B are type of stereoisomers. They are called geometrical isomers, and cis and trans exist whenever you have two substituents on the ring, not the three substituents. If you have three substituents on the ring, you no longer have cis and trans. So let's say if I have this, if I have this, and if I have that, you no longer can name it as cis and trans. Normally the cis and trans is included in the name. So you name your structure. This is the 1,4-dimethyl cyclohexane, and in front you have to point out these substituents, these two substituents. What is the relationship between each other? Are they on the same side or are they on the opposite side? If they are on opposite sides, then it's trans. If they are on the same side, it is cis. And again, I'm going to say this again. If you have three substituents on the cycle, there is no cis and trans. Okay, so let's have an example over here. If I give you this structure and I ask you, okay, let's go back to here. So if I give you this, if I if I tell you in the question that you have 1,4-dimethyl cyclohexane and I want you to draw all the conformations. So draw all the possible conformations of the 1,4-dimethyl cyclohexane. I didn't specify the cis and the trans. So the question is, let me write it down. Draw all possible conformations of 1,4-dimethyl cyclohexane. And the second part of the question, which one is more stable? Now the first thing I didn't specify, I have two substituents on the cycle, and I know that these two substituents can exist as trans and as cis. So when I don't specify, you have to consider both. As I said, you cannot go from trans to cis by rotation. So we're going to consider trans alone, do a rotation for the trans. A rotation for the trans will lead a trans conformer. And then consider the cis alone and do the rotation for the cis. And the rotation for the cis will lead a cis conformer. So you cannot have a trans conformer and rotate it and get a cis conformer. This is not right and not acceptable. So we're going to consider both types of stereoisomers, and we're going to start with the with either one of them, and then we're going to rotate and see if it's stable, and then we're going to go to the second one. We're going to draw its chair conformation and then rotate and see if it is stable or not. So let's start with the cis. We're going to start with the cis first. So I have the structure of the cis in here. The CH3s can either be pointing up or they can be pointing down. It doesn't matter. But pay attention. Every carbon should have two bonds in plane, one in front and the other one is behind. So if you have a CH3 pointing up, then the hydrogen has to be, it's not an option, it has to be behind. You cannot have a hydrogen and a CH3 in the same plane. This is not right, okay? Because you already have these two carbons in the same plane of the cycle. So let's start by changing this planar structure into a chair conformation. So draw your chair conformation. As I said, draw two lines parallel to each other. Just draw a point up and a point down, and then connect the whole thing together. This is going to be your chair conformation. Draw it like this. Now once you draw your chair conformation, now I'm going to put my substituents, label them where they are on the cycle. This is 1, 4. Start numbering wherever you want. I can start numbering from here to be carbon number 1, but I normally prefer to start numbering from here. This is 1. I can go by 1, 2, 3, 4 or 1, 2, 3, 4. It doesn't matter. So here I'm going by 1, 2, 3, and 4. So this is going to be my 4 over there. Notice carbon 1 over here has a CH3 which is up. You see it? It's up. It has to stay up. So to stay up on 1, it has to be on the axial position. This is going to make the hydrogen on the equatorial. On 4, that CH3 is up. It has to stay up. So on carbon number 4, the up position is the CH3 equatorial. So it has to be on the equatorial position. This is going to make that hydrogen on the axial. Go ahead and do the ring flip. When you do the ring flip, axials turn into equatorials, equatorials turn into axials. So this CH3, you're just going to flip that. So see that carbon? This carbon is up. It's going to become down. So this carbon now is down. The CH3, however, is going to stay the same. If it's up, it stays up. So now it's going to be on the equatorial. The CH3 over here is up. It needs to stay up. And now it is on the axial. So what did I do over here? I moved from an axial. So I'm going to go ahead and put that I'm having one axial CH3 and one equatorial CH3. Here I'm having the axial CH3 turned into an equatorial, and the equatorial CH3 here turned into an axial. So this is one axial. You need to check the percent of the axials with respect to the equatorials. The more equatorials you have, the more stable is your isomer. So here I'm having 50% equatorial, 50% axial, and here 50% equatorial, 50% axial. So the equatorial percentage is the same. So this is why I say that the conformers here, the two conformations, they are equivalent. They are the same. Each has one axial methyl and one equatorial methyl group, so they exist. They exist at equilibrium. So neither one of them is more stable than the other. So for the cis conformation, both conformers C and D have the same stability. Okay? Now for the trans. For the trans, this is up, this is down. Let's change that into a chair conformation. So I'm having this as carbon 1, this is carbon 1, this is carbon 4, this is carbon 4. So on carbon 1, my CH3, which is up, has to be on the up carbon here. The carbon is up, so the up position is the axial. And that CH3 is down. It has to be down. It has to be equatorial. So now, I'm sorry, axial again. So now I'm going to go ahead and flip it. To flip it, this carbon becomes down, and that carbon over here is going to become up. So this carbon up, this carbon down. And now the CH3, it's up. It has to stay up. It's now on the equatorial. The CH3 is down, it has to stay down. So now it's on the equatorial. See how what I moved by? I moved by one axial, There's no comma in here. So I moved by having my both groups to be on the axial position. And now both the groups are going to be on the one equatorial and one equatorial. So I have one equatorial CH3 and another equatorial CH3, and both are going to be on the equatorial position. The CH3s being on the equatorial position will not interact with any of the axial hydrogens because they are very far away from them in different planes. So that is going to make that structure more stable. The more equatorial positions the groups occupy, the more stable is your structure. Two equatorials versus two axials, so definitely this is more stable. Now, because a trans has more equatorials than the cis, than this one here, then I would say that the trans is going to be more stable than the cis. And in most of the cases, the trans is always more stable than the cis because the groups are the farthest away from each other. Now, let's go ahead and take a look. Let's go ahead and take a look here and see. Okay, let's go ahead and take a look here why this guy over here is not stable. Why it is not stable? Because if I draw its chair conformation, let me draw its interactions in this case. I'm having a CH3 on the axial position. It's up. Okay, that CH3 which is up is going to interact with all the hydrogens that are up. I have two carbons here that are up, then their axial hydrogens are going to be up. So I'm going to have a 1,3 diaxial interaction. This is 1, 2, 3. So 1,3 diaxial interaction with respect to the CH3 and the two hydrogens on the side, which is up. And then for the CH3 that occupies the axial, which is down here, this is the CH3, that is going to interact with the axial hydrogen that is coming down. These two actually axial hydrogens that are coming down, they are in the same plane as the CH3. So I have again two basically hydrogen CH3 diaxial interactions. So I have two hydrogen CH3 diaxial interactions in the top plane and two hydrogen CH3 diaxial interactions in the bottom plane. So that is going to increase my energy of the structure and decrease the stability of this type of conformation. So this is why the direction of equilibrium is towards the di-equatorial, because this exists in a higher percentage, like 99%, compared to the 1% of the two groups existing in the diaxial position. This is another example, trans. Now here I'm specifying trans 1,2-dimethyl cyclohexane, and I am asking you here, go ahead and find out which conformer from the trans is going to be the most stable. But again, the most stable conformer is the one that has the CH3s on the equatorial position. On the equatorial position. So change this into a chair conformation. My CH3 is up. So my CH3 is up here. So this is going to be the up. My CH3 on this carbon, I have carbon 1, carbon 2. This is 1 and this is 2. My CH3 here is pointing down, then this is going to be down. Okay, so now I'm going to go ahead and do the ring flip. Doing the ring flip, again, see that carbon? So doing the ring flip, it's easy. When you do the ring flip, the easiest way, point out these edge carbons in there. Make one, okay, just flip it. The down becomes up and the up becomes down. So see that up becomes here, down. And that down becomes here, which is up. So basically this CH3 is down. Do you see it? It's down. It has to stay down on this carbon. And this CH3 is up. It has to stay up. So it has to be on, I'm just going to draw it like this here. It has to be on the equatorial, because the axial, see, the axial is down in this carbon because this carbon is pointing down, and the axial here is up for this carbon. So it has to stay It's up, it has to stay up, so now it is on the equatorial. Now for this structure here, I'm having the two CH3s on the equatorial, so immediately this is going to be the most stable structure. Here I'm having the CH3s on the axial. They're going to undergo the one, they're going to have the 1,3 diaxial interactions. So it's going to be completely unstable. I'm going to have here interactions there between this hydrogen and this hydrogen. So these are down. They're going to interact with this CH3. And then with that CH3 over here, let's change the color. We're going to have a hydrogen which is pointing up, another hydrogen which is pointing up, and these are going to interact with the CH3. So I'm going to have 4 hydrogen CH3 axial interactions. Each one corresponds to 0.9. From where am I getting this? This is a special table for the chair conformation, but I'm going to give you the values for those so that you can easily calculate the energy. So I do have energy in this structure, and I do have another energy here in the equatorial, because the CH3s are 60 degrees apart. When they are like that, I have a static strain in here. It's gauche. So its energy is 0.9, but it's still less than the CH3s being on the axial position. So I can easily say that the groups on the equatorial, they are more stable than the axial. So this conformation is going to be more stable. This conformer is going to be more stable. These two conformers are not equivalent. Always make sure, if you have a bulky group, like a tertiary butyl group in this case, always make sure that your bulky group is always on the equatorial, no matter what. So here my bulky group is on the axial. Flip it, make it equatorial. It's down. See that carbon now, when you flip, that is going to become up. It's going to become this carbon here. Okay, and this carbon which is up, you're going to flip it, and that is going to become down here. This carbon is going to become up, but this group is down. It has to stay down. It is on the equatorial. Always make sure that the bulky group is always on the equatorial. You don't have an option. So that is going to be the most stable conformer between both. Last thing here I want to say, if you have a chair conformation and you want to draw the chair conformation into a Newman projection, how would you do that? Well, okay, so let me pull this up a little bit and let's have an example in here. So if I give you an example, okay, if I give you an example over here, let's draw this first. So if I ask you, go ahead and draw, so this is a CH3, this is a CH3, and that is an isopropyl group. Okay, that is an isopropyl group here. Let's make it behind. So I'm giving you this cyclohexane, and I am asking you, go ahead and change it into a Newman projection. Now I know that a Newman projection is between 2 carbons. So, and here I have 6 carbons, so I'm going to end up having 2 Newman projections that are separated by a CH2s. Okay? The way that I'm going to view this, there are different ways I can look at. But I'm just going to go ahead and explain the easiest way. Okay? Here you go. So let's go ahead and... So I'm going to change this, okay, I'm going to change this structure into a chair conformation. So as you can see over here, I changed it into a chair conformation. I don't like the drawing. Let me draw it in a better way. So here you go. So change it into a chair conformation first, and then from the chair conformation, we're going to do the Newman projection. Okay, so we're going to change that. Let's start by numbering it. So I'm going to number it as 1, 2, 3, 4, 5, and 6. On carbon 1, I have a CH3 which is up. So this is going to be my CH3 which is up. So this is up, this is down, and this is down. Up means my axial is occupied because this carbon is up, so this is going to be my CH3. On carbon number 2, my CH3 is down. It is on the axial position again because the down is on the axial. And then this is going to be 1, this is going to be 2, this is going to be 3, this is going to be 4, this is going to be 5, and this is going to be 6. So on carbon number 5, I do have my isopropyl group, which is down. See, it's on the equatorial because the axial is up. The hydrogen axial is up. Now, once I change this into a chair conformation, now I can change this into a Newman projection. To change it into a Newman projection, I'm gonna make this easy on you. I'm gonna look here, okay? I'm gonna look from this angle here, and I'm gonna consider every two carbons. Every two carbons are gonna make my Newman. Every two carbons here, I'm gonna make my Newman. So my Newman is gonna be between carbons 1 and 2, and between 4 and 5, and they're gonna be connected to carbon 3 and carbon 6. Okay, so let's go ahead and draw the Newman projection. So to draw the Newman projection, here you go. So I'm gonna go ahead and draw two circles like that. Okay, and right now what I have is my groups in here. I know that I have a CH3. Let me go ahead and draw a CH3 in here. This is gonna be a CH3. There's going to be the isopropyl. I'm going to fill the rest with the equatorial hydrogens. So this is going to be my equatorial hydrogen. My equatorial hydrogen is going to be pointed up because my axial is down. The axial hydrogen is down. The equatorial hydrogen is up. And then over here I have an axial hydrogen which is up. I have my equatorial hydrogen which is down. Axial down. Equatorial up. And then I have my axial hydrogen which is up over here. Now doing it like this, it's easy. Now you can see the Newman. See, you can easily see the Newman over here. So with the Newman projection, what I have is carbon number 2. If I am looking at this side, carbon number 2 is going to be in front, so that is going to be carbon number 2. Carbon number 2 has a CH3 which is pointed down. This is going to be my CH3, right? It has a hydrogen here. Okay, so the hydrogen is going to be on this side. This is going to be my hydrogen. And carbon number 2 is connected to carbon number 3, which is a CH2. So this is going to be a carbon number 3, and this is going to be a CH2. I'm just going to label that as carbon number 3. Now, carbon number 2 is here. This is carbon number 2 is in front, and carbon number 2 is connected to carbon number 1 at the back. Carbon number 1 at the back is a CH3. I'm going to use another color there. So carbon number one is a CH3 at the back. It's a hydrogen here. And then this carbon is connected to carbon 6. This is going to be carbon 6. This is going to be a CH2, which is carbon number 6 over there. So I'm done from the first Newman projection. Now for the second. For the second, I'm still looking at this side. So at this side, I have on carbon 4. So carbon 3 is connected to 4. Where is the 3? This is a 3 over here. So carbon number 4 is in front. And carbon number 4, as I'm seeing it, it does have a hydrogen down. This hydrogen here, I drew it. It has another hydrogen on the side, and it is connected to carbon 3. Okay, see how straightforward that is. So this is carbon 4, and carbon 4 is connected to 5. 5 is at the back, so this is going to be carbon 5 over here. Carbon 5 has a hydrogen which is on the axial, so this is going to be my axial hydrogen over here. This is carbon number 5, and it is connected to an isopropyl group. Do you see that isopropyl group in there? And then carbon 6. So it's connected to carbon 6. This is carbon 6. And then I have my isopropyl group. Just go ahead and draw it as you see it. This is going to be my isopropyl group over there. So this is the representation of the Newman projection for the chair conformation. So now when I see something like this, I know that I have 2 carbons here, 2 carbons here, 2 carbons here. So this is my chair conformation. Number your carbons. Okay, this is carbon 5. So number your carbons in here. I'm going to give this 1, 2. This is going to be 3, this is going to be 1, 2. 1, 2 are going to be connected to 5, 4. And then you have a 3 and you have carbon 6. Just remember that you do have between the two Newman projections, you do have two carbons in common, which is carbon 3 here and carbon 6 over there. So this is carbon 6 and carbon 3. So the Newman has to be between these two carbons and these two carbons if you are looking down from the side. If you are looking from this side here, I made the Newman between 4 and 5 and 2 and 1, and the connection is 6 and the 3. So it really depends where do you want to view your bonds of the Newman projection. The easiest way is to look at the bottom and write them like that. So now once you go ahead and you figure that out, I can easily number my carbons. So it's going to be carbon 1, this is 2, this is 3, 4, and 5. So I know on carbon 1 I have a CH3. The CH3 is up. Do you see it? So you put the CH3 up there. And then on carbon number 4, I have nothing in there. I have my hydrogens. Skip that. Carbon number 5, I have an isopropyl group which is down. So I have to write it down like that. This is on the equatorial position. Okay. And then on carbon number 2, I skip this. Carbon number 2 has a CH3 which is down. So I have to put it down like this. This is going to be my CH3.